keep rocking it. We in the house now. Get
So live editing of the live stream. Hello everybody and welcome to the 7th Stockholm Unity Meetup here at Toca Bocas. Hope everybody's well. You want to say something before we start, quickly? No, Andrea's fine. We're all here on Andrea's behalf of having this wonderful meetup group so we can come around and meet our Unity. You're currently at Toca Bocas, as we showed you in this video. We're a kids apps company, so we make apps for kids, which we like to call digital toys. So we make open-ended, free-play applications that embraces the pure play of children's activities. Today, me and Victor are gonna have a sort of a classic postmortem, which we're gonna talk about from one of our latest applications, Toca Nature, which was released this fall. So my name is Lucas. I will talk about game structure, rendering, and optimization during this talk.
And I am Victor, and I will mostly talk about AI, but I also work on animation systems and user interface interaction during the project.
Cool. So for everybody to be on the same page, we're going to show you the trailer for that game before we start the actual talk.
Toca Bocas!
No! No! I know that would happen. So... This one?
Yeah.
Awesome. Don't look. You're spoiling me. Stop looking. Okay. So one of the most predominant features in Toca Nature is the ability for kids to manipulate the terrain. There's two primary ways of manipulating the terrain in Toca Nature. When it's raise the ground, when it's lower the ground. It's not that much more complicated, but interaction works really well. So what I'm going to talk about now is a little bit how we implemented that in Unity and how we made it work for both high and low end devices, essentially, primarily on iOS. So the terrain is divided into a 4x4 segments along the map. Each consists now of a 10 by 10 subgrid, and each of those having 4 triangles, each representing that geometry. This structure is a little unconventional, but what we essentially do is that we take, whenever we manipulate this geometry, we do a special, we calculate the shared normals along that quad to create sort of an effect that each of these planes are actually a whole quad when they're actually not, which really supports the art style but doesn't actually have a real representation inside of the game. But yeah, it creates a nice illusion of those quads. We use these then 4x4 segments mainly to be able to divide up and freeze the geometry and only manipulate a certain part of the geometry whenever we need to. So we don't need to update the vertex buffers and everything as often as we otherwise would. So in this example you can see the red blocks being the AABBs of the meshes that represent that part of the geometry in that segment of the ground. You can see them going from red to green whenever they're disused. They're also never unlit at the same time. This is to distribute the performance over time on all the grids. For rendering the terrain, we primarily used a very common technique called splat maps. Splat maps are like, traditionally splat maps are a lot of different techniques, but the essential of it is having multiple textures on the same object and then selecting some sort of way of distinguishing which of these textures you're supposed to render. A very simple solution would be like have a binary mask in this case, who's like the mask will choose which of the textures are going to end up in the end result. But yeah, the basic principle is just having multiple textures in the same object. So what we decided to do was to use splat mapping in different ways. We used to place on the y-axis. So for the bottom part, which is the sand, which goes under the water and on the beach line, and between that and the grass, there's kind of a normal lerp sort of way, and then we have a more special way of doing the actual snow. The advantage of doing this in a shader is really that we never have to update any geometry or do anything fancy. We just write the shader and then we manipulate the terrain as we would, and we get the results we want. Without having any sort of loading issues, actually having to switch any of the assets during this process, which works really well whenever you're trying to edit something fluently, and we also don't have to manipulate anything else than the actual positions and the normals of that surface. It's great. The third layer in this splat map, the snow, is a bit more complicated. So as you saw previously in this picture, we used a pretty standard per vertex lerp for this between the sand and the ground. With the snow, we sort of just experimented really to try to find this, but there's two different sets of sine curves. There's difference curve, which is just like a scaled sine cos curve of the x and z axes of the geometry. And then we step that under a hard step of another sine curve set, which uses that previous input plus whatever offset really we wanted. And it creates on a vertex level sort of this pretty unique looking sort of, pattern, I would say. Which worked really well with our art style, since most things are hard edge, or actually everything is hard edge. Which also goes for the water we decided to do. So we did a fairly simple way of doing water, very sort of cartoony, but still fitting the art style. So the trick here is really to combine all of the different parts into the same mesh and then manipulating all of the vertices based upon their positions in the shader. So that you only have one draw call and then you have all your actual triangles sorted in that object. But it's a fairly easy way of creating sort of a nice cartoony water effect. Then I'm going to talk a little bit about the vegetation. So in nature, we use resources quite smart and sparsely. So we have 5 different kinds of tree brushes, each of them representing its own type of tree. Each tree type only has 2 variances of its model, plus its lot versions, but essentially it's just 2 different of the same tree really. But by using random size and angles of how they will be actually growing up and how it's rotated, of course, and the actual size and the size of the tree was kind of enough for us to actually get a dynamic forest in this perspective, which was kind of surprising to us. We initially planned to do a lot more trees, but find pretty quickly out that we didn't need that much more. Another thing that really helped us was using radiant random distribution, which is a lot fancier than it sounds a lot fancier than it is. It's just you use a circle and you plot a random point in that circle, and that's where you place the tree if there's no other tree in it. But that sort of model created an actual very natural looking sort of feel to where the trees ended up from your trail from your finger. Other sort of more animation tidbits. We For the growing of the tree, we use this pop-up animation that's driven by the user interaction when they actually draw out the trees. That scales the tree first in the y-axis, then pops it out to whatever size it is in the X and the Z-axis. This creates like a little bit of a mushroomy pop effect, but it looks really nice and it's very hidden when the user actually does it quickly. We had a similar effect for cutting down the trees in the beginning, or actually removing them, but in the end we realized it was a lot more satisfying to just like cut them down in the actual direction of where you're dragging, which was an easy kind of cool way of doing it. Last thing I want to talk about vegetation. What we also do is that we have a layer of sub-vegetation, or as we call it, sub-foliage. So Victor will talk a little bit more about this in the next segment, but each of these forests has their own set of sub-vegetation that grows with the forest. So I'm going to talk a little bit about optimization here. This looks very similar to the last one, but this time we're focusing on the blue boxes. So the trick here is really to try to, obviously when we're trying to render this, we're limited by the amount of draw calls we can do. And as long as one tree is animated, it has to be drawn its own draw call because it has its own matrix evaluation and it has to go through all the pipeline. However, what we do is that we group them together based on the segment whenever they freeze, and what the likelihood of those trees being edited again by the user is, and freezes them. And also distribute that over time. We can only end up with a max of 16 actual groups of trees to be rendered, plus whatever group is actually manipulated at a point in time. But it works out really well and performs very rapidly. And it works great. We only use Unity standard combined mesh functionality to do this, so there's no magic static batching involved. And of course, this system is mostly used for culling. So one way I'm going to talk about later in the rendering is that we're not using the mesh renderer component that much. We're using our own, but we're using graphics that draw mesh for most of our draw calls, which means that we have to call things ourselves. So if you call a function, it's going to draw it whether or not it's on the screen or not. But there was actually a benefit to that because we could now call more efficiently, and because we are now in control and we know things that Unity cannot know, like the length that the camera will never point up or things like that. We could actually reduce a lot of the calculations you need to do. Plus, you could be lazy, like use bigger squares or whatever you'd like actually to call it rather than just using Unities. Not necessarily, but it was a good optimization for us in this specific case to get everything done. So I'm going to have over to Victor to talk more about the biogrid.
Well, until now, we have been talking about direct manipulation that the user does. But now we're going to see a system that creates indirect manipulation. And we're going to see what this is. Basically, the biogrid is this set of spheres that are overlaid on the terrain. And they keep information of the direct manipulations that the user has done. So, for example, each of these biospheres contains information of the amount of water in that space of terrain, the amount of ground that there is, the amount of mountains, and each type of tree. And then with this information, each biosphere evaluates habitat. We just say, okay, if there is this percentage of this type of tree and this amount of ground, spawn this type of tree. And the same for animals. So to be more specific, if you place birch on ground, you will most likely end up causing the birch subfoliage to be evaluated through. And then with this set of meshes, we will add the subfoliage level, and also you will spawn the hare population, which is attached to the birch. And then just to see what the final habitat will look like with all the trees, the subfoliage, and the animals is this view. Then regarding the biogrid, the only real optimization that we needed was just to spread update, because we have 41 biospheres that need to evaluate all those habitats. So the easy way to just reduce the performance hit when evaluating all the habitats was just to spread which biospheres we're evaluating at a certain point. And you can see on the red lines the biospheres that are being evaluated. Then we are passing to the animals. These are the 6 types of animals that we have in Toca Nature. We are going to first go into see how the movement works. And basically the way animals move is through steering behaviors. The peculiarity of this way of moving in a game is that instead of computing directly the position that an object needs to be, you compute the force that you have to apply to your current velocity in order to go to that target. So for example, in here, if you have this particular animal that wants to go to that target, you would compute this force that would steer the velocity towards this target, and will end up with a smooth path like the red one. And there are different types of behaviors based on this steering of force that produce different types of movement. So for example, the seek movement just steers the velocity towards the target. The flee behavior steers it away from the target. And then another typical behavior is arrive, which just reduces the velocity as you approach your target. Then with all these basic kind of movements, you can do more complex kind of behaviors. Like for example, imagine that, well, in the game, the wolves pursue several types of animals. The way the movement of the wolf is computed is by applying this algorithm, which just tries to predict the position of the animal that is chasing, and then seeking that position. So if this would be the hare, for example, and the wolf will be seeking it, the force would steer it towards the position that you predict that the hare will be, creating this motion. And in the case of the hare, you would have the other way around, in which you would do exactly the same computations, but instead of seeking the target, you would flee from it. So with very basic notions, you can get very different behaviors. Then all this steering behavior was created by Reynolds to simulate behavior of birds, so flock behavior. And actually, the good thing about not computing directly the final position, but rather making it at a force level, is that you can compute several forces at the map, average in a certain aspect, like you want to flee more from a certain animal than to flee from another one, and then you will get your final movement. So for example, in this case of flock behavior, what it states this model is you have 3 types of forces: alignment force, cohesion force, and separation force. And what each one of these ones is the alignment force is just a force that steers the direction of the animal towards the direction of the animals that are in your surrounding. So for example, in here you would see the animal, and just you would average the velocities of all the animals around you, and just assign that velocity as the alignment force. Then the cohesion force is a force that goes towards the center of the group, and it just averages the position of the neighbors, and then is a force that goes from your position to that position, as you can see in the red vector. And then finally, the separation force is a force that steers away from the group center. And then, depending on how you add up these forces, so let's say you want to simulate a group of animals that are all aligned, you would give to this force a lot of value, while on the other forces you would have a lesser value. And then you will add up and average the forces. But right now we just have talked about the movement, but there is nothing that gives a target to each animal. And the way that this target, each specific target is given to the animal is through a finite state machine, which basically is a way in which you have different states, and each states represent a logic for the animal. And this is what, for example, when the chase is detected, it's in charge of executing the logic to make the wolf prosecute the hare, for example. And to see how all the movement is mixed with states. In here you see the migration state, And you see how when you delete a mountain, well, when you delete the wolf's habitat, they try to go to another habitat. And you see that all of them go in a sort of aligned way and sort of compact. That is due to the flock behavior that I described before. But the problem of steering behaviors and flock behavior is that since you apply the same logic for all your animals, there is no real distinction. So it's very difficult to attach to a particular animal. And what we had to do was to create a leader, which was basically adding on top of the movement the layer of if the leader is too far from you, just seek the leader. So then it would give the impression that this guy is trying to follow that when it goes far away. Like when it starts again, well, not in the correct spot. And the other thing that you can do with computations that you already have is, since you have the group center, if the animals are close enough, you can make them look towards the center of the group so that they feel connected. Because when they are together, they look towards the same spot. And finally, other things that we had to add to create a sort of connection between the flock was when animals go to sleep, they try to seek the closest tree. And what this makes is that you end up seeing clusters of animals sleeping on the same tree, which is quite cute and creates connection with the animals. Then in regards to how the animals interact with the environment, this is leg positioning. So basically, what you see on the image on the left is that animals tend to have their legs perpendicular to the horizontal plane. You see that when he's going upwards, they are perpendicular to the horizontal plane, and when he's going downwards, it's also perpendicular to the horizontal plane. And that is to lower the center of mass. And that's what we end up using on our animals. Like you can see there that the legs are always perpendicular. Yeah. Then finally, certain aspects of aging. Basically, the way we implemented aging on nature was through scaling the bones of the adult versions of the models. So what we did was, the younger the animal was, the bigger the head and the ears in comparison with the body. So you can see in here, the young fox has a bigger head in comparison with the body, compared with the adult version, which tries to sort of mimic what happens in real life. And then a good way of doing the aging like this is that it's very easy to animate the scale on those bones to make the effect of aging. Then finally, I'm going to end up with some aspects of optimization. As you have seen, there were like two views. One view that was the zoom out view in which you see all the world, and the other one in which is inside the world. The problem when being on the overall vision where you see everything, it was that the animals were a performance hit in terms of rendering. So what we did was to use the technique called level of detail, which just means you use a reduced version of your model for certain render like aspects. And in this case, what we did was when you are on the overall map, you will see rendered the reduced version. To do this, either the artist who is in charge of 3D modeling can do it, but there is a company called Simpligon, a Swedish company, which auto-titles themselves Automatic 3D Optimization that can generate this model for you. And then, for example, in our case, we went from the normal version of the animal to the loaded. It's almost like 70% reduction. It's 65 or something. Well, it depends on if it is by triangles, birds, or things. And then finally, since the use of different models happened when you were on the overall and in the zoom-in view, that had already the fading when you change. We didn't need to do anything to change the models. it's just a pop that happens, but since there is a white screen, you don't see any change. And then you don't really realize. Then finally, another optimization. Since you have the logic of a lot of entities, cache as much as possible transforms. I think in the new Unity 5, they cached the transforms, but until now this didn't happen. And it turned to be a performance hit to use transform dot all the time. Then the same, like if you call transform dot forward or right or whatever, those are not cached. So if you're gonna use several, cache it and reuse it. Don't have it, call it everywhere, because then you can have a performance hit as well. And also a small trick that we used was for the whiskers computation, meaning that to avoid collision against things, we raycasted in different directions. At the start, the computation of those rays was through using of cosinos and sinus, but that turned out to be a performance hit. So you can compute your vector perpendicular to another with this easy trick, which is just flip the components and negate one of those. And then, if you don't believe me, just do the dot product of these two, and you will see that it gives 0, meaning that they are perpendicular. And then this trick is also useful if you want to have not perpendicular, not at 90 degrees, but rather at 45 or lesser angles, by just averaging the initial vector and the perpendicular with a certain value. Like in this case, if you want a 45 degrees, just do the average between them two, and you will have the middle vector. And then finally, if with all this you have problems, like there were some functions that were a bit problematic still, just spread when that function is called, so that you will not have all the animals executing the same function per frame, which might not be necessary probably. Then I pass the turn to Lucas again.
Okay. Let's look at some pretty things. So, in Toca Nature, we use 3-point lighting system. I'm gonna talk a little bit how we choose to do that, but essentially we're using 3 lights. We have 1 key light, 1 fill light, and 1 ambient light. The key light and the fill light are standard directional lights. Really nothing fancy to them whatsoever. But ambient light, however, we got inspired basically by how Maya does its ambient light, where Maya has the ambient light sort of as a spotlight unless you're without certain reach. This is very useful for like having a sunspot or actually giving some direction towards where the ambient light is coming from, but still maintaining normal ambient light everywhere else there outside of the reach of that ambient light. What we did in nature was that we set up different light configurations for each sort of set of the day. So as you can see, we have fairly similar sort of ambient light over the whole day, but very different key and fill light. They also don't, for instance, night is not as long as other times of the day, because kids in general don't like when there's night. There's not much to do when there's night, everybody's sleeping, right? So, yeah. And all of that combined, over time, we lerp those values and slurp those values depending on their properties. Again, just started to create our light cycle, which looks something like this. Yeah. On mobile device, however, it's pretty hard to get that many lights and shadows in, so we had to do some things just to get over it, really, performance-wise. One way of doing this is by bypassing Unity standard lighting models and just use their property keywords instead. This allows you to do things like pre-multiply alpha as intensity, for instance, which means that in your components of your light, you don't actually need to mold that against intensity, the distance of the object. You just have that already computed for you, which is useful in this very specific case. Another thing that's very obvious in nature probably is that everything is per vertex, right? That is not necessarily faster, because your number one bottleneck is your bus on a mobile device, and the more hard edges you have, the more verts you have. So there's a balance there that worked very well for us. And the last part down here is basically our entire computation for how we do the light in nature. It's not really complicated. We just have the 3 different lights. The only thing that diversifies is how to do the Maya-inspired spotlight we have a max over the actual range of the ambient light, which we actually just put in the alpha channel, since that's not really used on the ambient light, since it doesn't have an intensity, because it's an ambient light, right? And apply that to each vertex. I'm going to talk a little bit about our skybox, because we were really proud of our little beautiful skybox. So it's not really a skybox. It usually never is these days, is it? But it's an inverted half sphere, whatever that means, that we colored from white to black to the bottom, which helps us with the actual gradients of the sky, and also helps us with different camera angles, depending where you're looking at it from the world. That we texture from the inside. So there's basically 3 different passes that happens inside of the skybox. There's the skybox texture, which lerps itself over itself, and then we have the half sphere color, which is pretty much static. And then we take our lighting and we invert it so it's like being on the inside of a balloon looking out, essentially seeing all the lights projected onto the sphere. And when you trilinearly lerp all of these colors, you end up with what we use as our skybox in Toca Nature, which is quite beautiful. So, last thing I want to talk about is our photography, our photos. The photo feature that you can take. This is a pretty common feature to Toca Boca apps. A lot of our apps does this, where you can go in and you can take your own photos and get saved into your camera roll, and you can use them later to share them on Instagram or whatever you like. But in Nature, we thought that it was time to do something even more of this. We were inspired by Tearaway on PS Vita, which sort of embraced that even more. Maybe we could like customize images and stuff afterwards, but we really wanted these pictures to look beautiful. So essentially what we've done here is that we took our chance, because it's kind of allowed to take some time to load that photo, and so we applied some post-processing effects to this, which you usually can't on a mobile device, but in a specific scenario you can. So we used Unity standard depth of field and bloom effects. These were also connected to the light profiles, so these all settings are changed during the day. Because it turns out if you have the same bloom during night as you have during day, you're not going to see anything during day if you take a photo, right? And then if we can afford it, depending on the device, we super sample it twice or 4 times to render it really crisp and nicely. As I said, this means also that the rendering can take like between 1 and 4 seconds, but it's actually you accept that in the event of taking a photo in the application. And they're all Instagram sized, of course, because that's the new standard, right? And of course, there's the Toca Nature logo always embedded into that photo, so you can't share it without anybody knowing how beautiful your app is. Yeah. So this is the team that developed Toca Nature. If you can figure out what this thing in the middle means, that means you're a smart person. Or a nerdy person.
Helium person.
Yeah. Helium person. Helium person. Too many clues. Okay, thank you. Questions? Sir.
Hey, first off, that is a very beautiful skybox.
Thank you.
Secondly, what did you use for pathfinding?
There was no pathfinding.
Just avoidance. Or,
yeah, exactly. One of the nice things about the string behavior is that you don't necessarily, you usually don't have a global recomputation of your path, but rather you set the target and then you avoid or you react to the things that happen to your environment.
Yeah, cool. Thanks.
I believe he was first. Sorry.
I didn't really understand my ambient light thing. You talked about the ambient light have a range. What does that mean? We have several ambient lights with like.
Yeah, so from what I understand as a programmer, which maybe I shouldn't speak that much on Maya's behalf, but from what I understand in Maya, if you plot down an ambient light in a Maya scene, you have a range parameter on that light. And what that means is, from what the documentation said at the point of my reading it, as I remember, is that within the range of that ambient light, it's going to act as a spotlight, but everywhere else outside of that is going to act as a normal ambient light. So if you if you only want normal ambient light, like the way Unity does it, you would just zero that. You would have like this constant color everywhere. But it has sort of a nice feature, like actually giving some. It gives you a better sense of the area when it actually functions as a spotlight in certain place. Maybe I should have taken better pictures of that, but it's
So it doesn't become as flat.
exactly.
But
So
you
it's
still only have one ambient light in the entire scene.
yes.
Yeah, I'm a bit curious about the numbers. That is, how much did you gain by these optimizations? For example, like that you don't update the whole mesh and the culling and.
Enough to run 60 frames a second on iPad 2.
That's good.
Yeah.
Still, I mean,
Yeah,
how
not
much
really.
difference does it
45 at
make?
max
45,
out
yeah.
cap.
Yeah.
That's max out cap. So that's what's like with as many things in the loop as possible. So we didn't actually. It's probably my fault. I'm not really good at doing progressive measurements of our optimizations. We tried to reach our frame rate goal, and once we reach it, we're sort of happy. I can say for sure the thing that gave us the most back was when we did the distribution of updating the meshes. We also have a collision mesh that has to be updated with them. We figured out a way, it's not really complicated, but to never have one of them update on the same frame as another one, because then they can just slip in under the frame rate, each one of them. So that was probably the most effective optimization. The other optimizations that really worked well was the one we did in AI, you talked about, in terms of map optimizations. I think we half-folded our computation time once all of them were applied. You can do really, with math and Unity, especially on 32-bit ARM devices, you can do some really weird things if you want to get really deep down. If you do a lot of these trigonometry things, like it's actually cheaper to take the length of a vector and divide it yourself in C# than use the normalize function. So there's a lot of these things you can find out that's very specific that gave us, like that was a 25% boost, but it doesn't really tell you anything about anything else. That just happens to work there. So here we try to talk about the general ones that we think applies. But I don't have any numbers, sorry. Simplegon's great though. They have good numbers.
Okay.
Yes?
Yeah, other than Unity, what tools do you use to make this kind of game? Like Maya and what other programs?
Maya? Photoshop? What do you use, Morten?
It's all in here.
So-
But you code a lot of outside of Unity.
Oh yeah. Simplegon is the number one third-party tool that we use within Unity to do this application. I mean, there's not that much else than Maya and Photoshop, I guess. That's what Jonas uses for his art.
Actually, I'm a bit curious about the Simplegon. Why did you choose Simplegon over Maya's built-in reduce function?
Primarily because I didn't know that existed.
But we got free tickets to use Simplegon.
So we can promote it.
Yeah.
No, I mean, I don't know if Maya has this or not, but the one thing that was huge for us was that it could do bone reduction. So essentially, it takes the same model without manipulating your animation data and reduces the amount of bones in the mesh, and it ends up looking okay and even good at long distance. How that happens, I have no idea. That's beyond me. But that feature alone is really good. I don't know if Maya has that. I can't.
Simplegon. That's why I'm curious why you guys went with it.
Yeah, I don't know if one of our artists wants to answer
Well,
about the reduce function in Maya, but
the Maya stuff sucks.
I'll show you guys some tricks after.
I'm guessing you can mark some bones as not removable because you scale them for aging, right?
yes, but those bones you can mark them, but those bones we do scale, they tend not to be the ones that gets removed anyway.
But it was more like even once we did the reduce, the loaded version, we tried it out to see if the animation or the scaling for the aging really affected them. So it's not that it's perfect. You have to try and seek the best combination, because it might be that the bone reduction is too much, and you end up with a really choppy animation that even in a loaded version you can see.
Yeah.
Actually, you can see if you pay attention on the deer, he has a quite choppy on the loaded version.
Yeah. He only has one limb per leg with
Yeah.
easy walk.
Yeah, it stinks.
Works great though when it's 14 pixels high.
Yeah, how long was the time frame for this project, would you say?
So this one was 7 months, all in all. I mean, live production was about 6, I think. Emil, do you know?
You stopped working on a view,
Yeah.
and then you start before Christmas, maybe some prototyping.
Yes.
I would say
But we started coding end of January.
Compared to other projects, is that long for you, or is that...
I can't answer that.
Or is it just the equal as the same?
Well, I would say most of our apps, the actual development time is between 6 and 8 months. So this was sort of a tight deadline.
Yeah.
With this scope of it. We're very ambitious in the solutions, which I'm glad.
Very ambitious in this case. So yeah, but I would say it's a bit. It's about the same length as most of our projects are nowadays. Yeah.
Can I have another one?
Yeah.
Sure. How do you go about with the teams? Do you continue working on a new product with the same team, or do you how do you go about that?
So usually we keep on sort of the same people in each team for each product, but some of our resources are sort of liquid, move in between teams, and we have changed people in between teams. But the core team is usually the same. Thank you. Great. So, shameless plotting. Please come join us. We're looking for 3 developers right now in the gameplay area. So we're looking for 2 juniors and 1 lead developer to take on one of the teams this gentleman asked about. Also in the future. We're also looking for technical competence in the mobile space to take care of something we would like to call the tech team. So if you're not that into game development in Unity, but still like it's an awesome company and I'm really good at Android, or really good at iOS, or really good at Windows, or all of them, please come talk to us. We have plenty of work for you to do. Yeah. Or just come talk to anybody with these Toca pins afterwards. Great.
Can I have one more question related to that?
Yep.
Do you actually release your games on Android?
Yes.
Okay. So, but I think in the beginning of the presentation you mostly said like iPad and iOS.
Yeah. So, yeah, we're iOS first, obviously, judging from this presentation. And this presentation especially was we tried to push as much as we possibly could within the time frame we had, which means that we're also looking very hard at the hardware that we're working with during that time period. But yes, we do release our products on Android. I believe Nature is coming up fairly soon, but I can't say anything about that really. Great! Any more questions before I go to the next slide?
What about Windows 8? Do you release to the market there?
Yeah, I believe we have, Jonas, how many apps?
Which one?
Windows 8?
Klaus is better on that.
Window.
We're all here.
Currently we have 4 apps out, with more coming along the way.
Yes.
So if you have a Windows phone, now is a good time to make kids, make children.
He's obviously the brain behind this game, so I'm saying. Oh, thank you everybody.